Alright, let's take a look at this problem here. We have this circuit, and we're told to find the input impedance of this circuit, which is Zn at this point here. And we want to assume that the circuit operates at omega of 50 radians per second. Alright, so the first thing we want to do in solving this problem is we want to put everything in terms of impedances. So we'll keep this capacitor here as one impedance, and we'll call this Z1. Call this guy Z1. And then we're going to take the 3 ohms and the 10 millifarad capacitor that are in series, and we're going to call this our second impedance component, Z2. Okay, and then the third part, we're going to take this inductor and this resistor and call that our third component, and these also are in series so we can combine them. So this is going to be our Z3. Okay, so that's the key here, is to be able to combine these components and just come up with an equivalent impedance. So essentially what we're going to be doing is we're going to be taking Z1, Z2, and Z3 and combining them to get just one final Z input impedance. Okay, so let's go ahead and do this using what we've learned thus far with phasors and the phasor relationships with these circuit elements, as well as looking at impedances and admittances. Okay, so one thing to note is the reason why we're doing phasors is because our calculations are going to be much simpler, but it does not necessarily mean we're going to do less calculations. It'll be some math, but it won't be as complex. Okay, we're not dealing with derivatives or integration at this point. So let's go ahead and write this out. So for Z1, we're going to have just one capacitor, and if we put that in impedance format, remember that the capacitor impedance is just going to be 1 over j omega c. Okay, that's just by definition. So all we have to do is plug in the values. So we got 1 over j omega, we said was 50, and then c in this case is 2 millifarads, so that's 0.002. If we do the math here, that's going to be 1 over j times 0.1. 1 over 0.1 is just 10, so that's 10 over j. And we know 1 over j is a negative j, so we can rewrite this as minus j 10 ohms. Okay, so we've got our first impedance right here for Z1. Next thing is we want to determine our second impedance, which is Z2. In this case, it's a resistor, and remember, a resistor is just going to take on its own value, so it's just going to be 3 plus we have another capacitor, so the same thing, 1 over j omega c. We'll just plug in the value, so I just write this a couple more times. 1 over j omega is 50. In this case, its c is 10 millifarads, so that's 0.01. Okay, we rewrite this some more. I'm just taking it step by step just so you can see what's happening. 0.5, and that's just 3 plus 2 over j. Again, 1 over j is a negative, so that's where we get 3 minus j2, and the impedance is in ohms here, so we got the second part there. So we got Z2. Let's look at Z3. Z3 is going to be, we have an inductor as well as a resistor. So let's just put the resistor value 8 plus the inductor is going to be j omega L. So we're just plugging in 8 plus j times 50 times L. L is 0.2 henries, and that's just going to give us 8 plus j 10 again ohms. So we've got the three impedances here. Okay, so we got Z1, Z2, and Z3. So we can technically redraw the circuit if you wanted to. Let's just go ahead and do that. So I got one impedance element here, another element here, and the third one here. Where we got Z1, Z2, and Z3. And we'll see, we want to combine all these, and we'll see that Z2 and Z3 are in parallel. We want to combine those, and then we'll get the third one, Z1 here, is going to be in series, so then we just add that. So, and that's going to give us our equivalent. This will give us our Zn here. So let's go ahead and write that. So to get Zn, that's equal to Z1, which will be in series with the parallel combination of Z2 as well as Z3. And we rewrite this, that's just Z1 plus Z2 times Z3 over Z2 plus Z3. Okay. So we just need to plug in those values. We already determined what each one of those values were. So let me go ahead and put that in here. So we said Z1 was minus J10 plus Z2 was 3 minus J2 times Z3, which was 8 plus J10 all over 3 minus J2 plus 8 plus J10. Okay, we can rewrite this here. Let me scroll up. So we can rewrite this down here. So Zn is equal to minus J10 plus, let's just leave this here. This is just multiplication. I'll just leave it here. I'll do it on the side. J10 over, the denominator is going to be 11 plus J8. Okay, so let's take a look at this part here and then solve it on the side. So let's just say we're going to solve it over here on the side. It's just a matter of doing the multiplication there, and what we'll get is 3 times 8, we got 24 plus J30 minus J16 minus J squared 20, and remember J squared is just a minus 1, so we'll just take this guy here and substitute that here. Okay, so it's just again plugging in 24 plus J30 minus J16 plus 20, and then further adding them up, we get 44 plus J14, and that's what we get for that numerator now. So let's go ahead and rewrite this guy up here. We got 44 plus J14 over 11 plus J8. Okay. So we can go ahead and solve for this problem by multiplying by the conjugate of the denominator. So I can take 11 minus J8 and multiply it by the numerator and denominator, and what we'll get will be so let's go ahead and rewrite this. Oh, I forgot, actually, I forgot. We still have the minus J10 here, so make sure we don't lose that. So let's rewrite this. We still have the minus J10, and then we have plus 44 plus J14. Actually, let me write this on the bottom here. I'm going to write it down here. So minus J10 plus 44 plus J14 times 11 minus J8 over 11 squared plus 8 squared. Okay. 11 squared plus 8 squared, if we plug that in, that's going to give us 185 in here. And then the same thing we did for the previous one, we can do it again down here on the side. 44 times 11, 484 minus J352 plus J154 minus J squared 112, and double check my math just to make sure I did that right. If we do that, if I continue to do that, I get minus, scroll up just a little bit. We rearrange these numbers. Okay, 484, and then this again becomes a positive 112. So this becomes plus 112, and then we combine these two guys together, and we bring it back to the numerator over here, and essentially what we do, we get, after we divide by 185, so I'll let you do the rest of the steps here, but essentially what we get is, eventually we get minus J10 plus 3.22 minus J times 107 ohms, and this is going to be again RZN. We can simplify it some more, and we get 3.22 minus J 11.07 ohms, and this is our input impedance, and this is our final answer here, what we're looking for. Okay, but I want to back up a little bit, and I want to do another method from, instead of multiplying. So what one method that was done here is, I'm going to say this method here, I'm going to write here method 1. I'm going to do method 2 down here. So method 1 was multiplying the numerator and denominator and keeping it in this rectangular format. Method 2, I want to switch it to polar format. Okay, so let's just say we have minus J10 plus 44 plus J14 over 11 plus J8. Okay, so I'm taking this part here, and I'm just going to rewrite it down here and take a different a methodological approach. And it's all up to you what you think is easiest for you to do. And what I'm doing is, let me scroll up, I'm using the properties of going between rectangular components and polar components. So remember, our R, our angle, our phi is going to be tangent inverse y over x. And also I'll go ahead and write this down. Z1 over Z2 is just R1 over R2, and then our angle is going to be our angle difference from the first angle minus the second angle. That would be our polar format. So if we do that, let's just say we take the numerator, call that R1. If we take that, that's going to be 44 squared plus 14 squared. If we do the math, that's going to give us 46.17 roughly. Take tangent inverse of 14 over 44, and that's going to give us our angle, first angle there. We plug that in to the calculator, we get 17.65 degrees. We do the same thing for the denominator. Denominator, we get the square root of 11 squared plus 8 squared. That's going to give us roughly 13.6. And then our second angle is just going to be tangent inverse of 8 over 11. And that's going to give us roughly 36.03 degrees. Okay. So we can rewrite this. We can rewrite this component of the impedance in polar format. So we can rewrite this as 46.17 at an angle of 17.65 degrees over 13.6 at an angle of 36.03 degrees. Okay, and then so essentially what we do is we have this format here. So R1 over R2, we just divide them. If we divide that, we get, so this will equal 3.39. We subtract the angles, which is going to give us minus 18.38 degrees. And now from here, we want to take it back to rectangular format. Again, this is all preference on what's easier for you. Again, the first method is one way of doing it. This is another method, depends on what your preference is. But remember, to do that, x is equal to our cosine, our angle. You can call it theta or phi, whatever you want. I'm going to call it theta just to be different, not to confuse it with the other ones. And y is going to be r sine theta. Okay, so if you do that, we get x equals r is 3.39 cosine minus 18.38 degrees. Okay, and that's going to give us 3.22, and then y is going to be 3.39 sine minus 18.38 degrees, and that's going to give us minus 1.07, minus 1.07. Is it 1.07 or 11.07? Yeah, it's 1.07. Yep, 1.07. All right, so now if we look here, if I did it all correct, this here, x is 3.22, is the same as the 3.22 from method 1 up here, and then minus 1.07 is our imaginary component. It's right here. So that's just another way of getting to these conclusions. Possibly one may be longer than the other, just a preference. And now I'm going to plug that back into our equation here. So we got minus J10 plus 3.22 minus J 1.07, and of course if we solve that we get what we got previously, which was 3.22 minus J 11.07 ohms, and this is our Z input impedance, and this is our final answer. So two methods or approaches to come up with the same conclusion here for the equivalent circuit that was given to us from the previous circuit up here. Okay, so that's how you apply this. It takes some time, but as you can see, the math is quite simple. Okay.